Hi, my name is Bill Kinney. I'm a professor at Bethel University, and this is the first of a series of videos that I'm making on geometrically interpreting the chain rule in multivariable calculus. So what is the chain rule? Well, first of all, here's the situation that we're going to be applying the chain rule in. The chain rule is used whenever you want to differentiate a function that is created by composing two other functions. And in this diagram, what I'm trying to emphasize here is that I've got two functions, one named phi or phi, whichever you prefer, and one named f. And the domain of phi is the plane R2. R2 stands for two-dimensional space. Its codomain is R2, which is also the domain of f. And the codomain of f is R, meaning, okay, look at this again here. Phi takes two-dimensional inputs and gives you two-dimensional outputs. And then f takes two-dimensional inputs and gives you one-dimensional output. As with all my videos, I recommend that you feel free to pause it and take notes and really think about what I say. It's sometimes hard to pay attention with videos like this, I know, but if you haven't been in that habit, that would be good to start now. So that's the type of composition we have. If we write variables, we could say that z is f of xy, and xy is phi of uv. In other words, we could treat uv like they are an arbitrary point in this set right here, that domain for phi. That point uv gets mapped to the point xy, which we think of as being in this set right there, the codomain of phi, but that's also the domain of f, which we emphasize by saying, okay, now xy gets plugged into f to give you finally at the end a number z, which is a real number right there. Sometimes you'll see people abuse notation, and instead of writing what they should write here, x equals phi of uv, little phi of uv, and y equals psi of uv, sometimes you'll see people not write the little phi and the psi, and just write x equals x of uv and y equals y of uv. Technically speaking, that's abusing notation because you're using the letter y here, for example, to represent both a function name and a variable, but usually that abuse of notation doesn't cause too much trouble. The composed function then can also be written this way as f circle phi. So the circle represents function composition, and what it is it's in with the variables in there, it's written like this: z equals f of capital Phi of uv, which equals f of the components or the coordinates of capital Phi, which are little phi of uv, comma, little psi of uv. What is our goal? Our goal is to find the partial derivatives of this composition with respect to u and v. Z depends on x and y, but x and y depend on u and v. Can I write the partial derivative of z with respect to both u and v in terms of, well, that's what these symbols represent, the partial derivative of z with respect to u and the partial derivative of z with respect to v. Can I write those in terms of the derivatives of the pieces that make up the composed function? Might be helpful to recall the chain rule in one variable. If y is a function of u and u is a function of g, then ultimately y can be thought of as a, u is a function of x. Ultimately then y can be thought of as a function of x, and you can differentiate y with respect to x. In this way, the derivative of y with respect to x is the product of the derivative of y with respect to u with the derivative of u with respect to x. I don't want to prove the chain rule in any way. I just want to show you what it says, and then we want to interpret it in the context of a situation here. In the given multivariable calculus context, what does the chain rule say? We want to find the partial of z with respect to u and also the partial of z with respect to v. It's a bit more complicated. Again, z depends initially on x and y. That's what this says up here. So we need the partials of z with respect to both x and y, but both x and y depend on u and v, so we need to have two terms here, first of all. And we also need to multiply each of these partial derivatives of z with respect to x and y individually by the corresponding partial derivative of x with respect to u and y with respect to u. It is somewhat analogous to what you see up here, and in fact, even though this is technically not correct, you can sometimes imagine up here when you're looking at this thing that these Leibniz notation symbols for the derivative represent fractions. In fact, many scientists do pretend these represent fractions. And you can remember this chain rule by saying, okay, if I'm pretending these things are fractions, then I can think of the du's as canceling and leave me with dy dx when I do that multiplication. That doesn't quite work here. When you look at this thing, you might imagine the dx's canceling, the partials with respect to x, and the partials with respect to y canceling, but it doesn't quite give you what you would think. If you do that, it doesn't give you 2 times the partial of z with respect to u. Instead, it just gives you the partial of z with respect to u. Look at this thing, pause the video probably, and contrast and compare. The only difference is we're differentiating with respect to v, so we have that on the bottom instead of the u. All right, running low on time in this first video. Here's the situation we want to try to think about the chain rule and interpret it. And let's see if we can consider this first general situation. What does the chain rule say in this situation from the symbolic perspective? What do we have here? We've got a function f. It's this function right here, though I'm initially just going to think about this without its formula. And capital Phi is a function or transformation that is a particularly important kind of transformation in multivariable calculus. In fact, it's a transformation that converts polar coordinates to rectangular coordinates. In other words, it's this equation right there. If you want to focus on the x and y individually, x equals r cos theta is what the little phi of r theta is, and y equals r sine theta is what the little psi of r theta is. R and theta are representing what u and v did up here. So just realize that. And that means if I do some copying and pasting, I can immediately get what the general situation looks like. Just replace the u's with r's and replace the v's over here with thetas. Oops. Copy and paste here. But it is also helpful in this situation to actually find the partial derivative of x with respect to r, y with respect to r, x with respect to theta, and y with respect to theta. If you look at the formulas up here, you can find those partial derivatives. So let's go ahead and do that here. Copy and paste this over, and I'll replace this thing with the partial derivative of x with respect to r. Look at this formula here. Differentiate that with respect to r, treat theta as a constant, you're going to get just cosine of theta. So this thing right here becomes a cosine of theta. The partial of y with respect to r, look at this formula. Treat the theta as a constant, differentiate with respect to r, you're going to get a sine of theta. Now let's go over to this one. What's dx d theta? Look at this formula, treat the r as a constant now. Differentiate with respect to theta, you're going to get a negative r sine theta. And finally, the partial of y with respect to theta, look at this formula right here. Differentiate that with respect to theta, you're going to get an r cosine theta right here. Final thing I want to say in this introductory video is that something interesting happens in this context with this particular kind of phi that transforms polar coordinates to rectangular coordinates. And that is, we can think of this as a dot product of two vectors in kind of a nice way. A little bit of thought reveals you can think of this as the dot product of this vector with, in fact, the gradient of f. Just write it like this. That's pretty interesting. That might lead to some nice interpretations of this partial derivative in this context. And with this other one, if you think about it, you can think of it as the gradient of f, not dotted with this one, but dotted instead with negative r sine theta and then r cosine theta. Maybe pause the video, take a moment to think about these things. And well, this is going to be the end of this video. I'll continue with this example in the next video.